All right, so we're talking about calorimetry here, the study of heat exchanges. And what we're going to be doing is just practicing some calculations for a lab that we're going to do, calculating heat of combustion of a candle. And here we're going to be talking about calories per gram. So again, we're talking about heat transfer. So let's say here I have this candle, and I'm going to light that candle, and I'm going to use a calorimeter, which again is a device used for measuring heat. And the idea of this calorimeter is just going to be a test tube, and I want to get an ideal calorimeter. All of the heat from this burning candle would go into my water, causing that water to change in temperature. I could then plug those values into my specific heat equation and calculate how much heat energy was gained by the water. So again, this would be a perfect scenario or a perfect calorimeter. All of the heat would either transfer into the water or would be accounted for somewhere else. So our calorimeter isn't going to be perfect. We're going to work through some of the calculations that we're going to do. So if we look over here, we see the data that we're going to be looking for. This is the data that we're going to collect in our lab. So first thing we're going to do is measure 10 milliliters of water and measure its mass. So we measure its mass, let's say it's at 9.72 grams. All right, then I'm going to measure the temperature of that water. I need to know where that water starts at so I can measure its change in temperature. And it'll be pretty close to room temperature, 21.8 degrees Celsius. Again, it's important to record all the digits that I know for sure plus one guess. So with our regular thermometers, we're going to record down to the 10th position because there are lines at the 1 degree marks. So 21.8 degrees Celsius. The next thing I have to do is measure the mass of the candle. Certainly I'm not going to burn this entire candle away. I'm only going to burn a portion of the candle. And I need to know how much of the candle burns so I can calculate calories per gram. So I need to measure that candle wherever it starts. And we'll say it starts with a mass of 38.78 grams. All right, the next thing I'm going to do is light this candle. Well, obviously I'll set up my calorimeter, but I'm going to light this candle and leave it right underneath my test tube of water. Again, the idea is to transfer the heat energy from the candle into the water, and there I can measure the heat or calculate the heat. So I'll do that for a minute or so, blow the candle out, and measure the highest temperature that the water gets to, and that is 87.2 degrees Celsius. After it is heated up all the way, it's 87.2 degrees Celsius. The last bit of data I need is the mass of the candle after it has burned, right? Because as I burn it, some of that wax is going to be going through a combustion reaction. Most of it is still going to be left behind in the candle. The difference between the starting mass and the ending mass represents how much of the candle actually burned. So after I burned that candle for a little bit, it then had a mass of 35.58 grams. All right, so now I've conducted my experiment. I've collected all of my data. Now it's time to crunch some numbers and figure out what it means. So I need to calculate how much heat in calories, that's food calories, was gained by the water. So I need to use my heat equation, Q equals mc delta T, and I need to make a variable chart. Q mc delta T. All right, so Q, that is heat energy. That's what I'm trying to find. That's what this question asked me for. Mass. Again, this is water. So I have the mass of the water. I have the starting mass of the candle, the ending mass of the candle. I'm only concerned about water. So that's 9.72 grams. C. Remember, the variable C represents specific heat. So we know the specific heat of water is 0.184 joules per gram degree Celsius. And then the last thing I need is change in temperature. So 87.2 degrees, which is where it ended, minus 21.8 degrees, which is where the water's temperature began, gives me a watt temperature of 65.4 degrees Celsius. Now that my variable chart is filled out, all I have to do is plug in my values. So Q equals M, which is 9.72, times C, which is 4.184, times delta T, which is 65.4. And that is 2,659.72 joules. Again, Q is heat energy. My specific heat was in joules per gram degree Celsius. Grams cancel, degrees Celsius cancel. I am left in joules. But this question asked me for calories. So now I have to use dimensional analysis to convert those joules to food calories. So I'll begin over here, 2,659.72 joules. There are 4.184 joules in 1 small calorie. And there are 1,000 small calories in 1 food calorie. If I multiply 2,659.72 times 1 divided by 4,184, that gives me 0.636 calories, food calories. So that's how many calories were transferred into my water. So the next question, number 2, asks me to calculate the heat of combustion in calories per gram. So I know this is the number of calories that I produced, but to get calories per gram, I have to divide that by the mass of the wax that was burned to produce it. And that's where these values come in, my starting mass and my ending mass of my candle. And all I have to do is divide. So first I have to find how much of the candle actually burned. To do that, I would find the difference between those. And this really should be an 8, not a 5. I'm just going to change that real quick, or my data is going to be a little strange. So it should be 38.58, my ending mass. I made the data up anyways. You'd be obviously collecting your data in the lab. So 0.636 calories, that came from this calculation over here, number 1, divided by 0.2 grams. And that's 38.78 minus 38.58. So if I take those values, 0.636 divided by 0.2, and I get 3.18 calories per gram. So that's how many calories of heat would go from my wax as it's released in a combustion reaction into my water. If I burned exactly 1 gram of wax, that's how much calories, or how many calories could be transferred in, according to the calorimeter that we designed to collect our data.